There's a few things I want to do today, and I want to, beforehand, review some things that I thought were interesting that I saw yesterday in lab, and problems that, as far as I know, nobody's shown me any solutions to. And at least one, I think, is a really nice contrast to the one we talked about last time. Last time we talked about this problem. This problem is notorious for looking better theoretically than it actually turns out in practice. When you try to implement this, as you're supposed to do on your problem set, most people cannot find many cases where this really does start showing its better behavior. And that's interesting. And I spent a lot of time stressing that in this class so far. Oh, algorithms is theory, and there's engineering, and partly because a lot of you are more from the engineering side than you are from the math side, and that's what computer science is about. But the truth is, the really cool stuff in algorithms isn't the hammerhead theory, which doesn't work in practice, but is the really, really practical stuff that people just overlook for years, and then somebody goes, huh, here's a good way to do it, and it's just a lot faster. That's the really cool stuff. So where do you see that? Well, that doesn't happen as often, but you still do see it. And one example, I think at least a good metaphor for an example, is a problem, an optional problem on your problem set. So now, I didn't get a chance to re-look at the one I actually put down, but I think it was this one. Did I tell you there's 3 arrays? Yep. And you have to figure out whether some 3 add up to 0 or something? Is that it?
Yeah. 1 element from each array.
1 element from each array, 1 from here, 1 from here, 1 from here. Find a triple that adds up to 0. OK. Now, I asked you to do this any way you could. How many people have tried this problem? Raise your hands. Anybody try this? Did anybody get an n-squared solution for this? No one. OK. So I think maybe it's time for me to show you an n-squared solution for this, since there's only one day left in this problem set. And I like to talk about it because it's a really cool problem that just a little cleverness, a little sweat, and boom. This isn't like the k log k. This really does work faster. And you'll see why. It's just a neat idea. So here it is. You have these 3 arrays. Let's just make them up. 3, 6, 9, 12, 15, 2, 5, 8, 13, 17, minus, minus, plus, minus, 1, 3, 5, 10, 15, minus, minus. OK. Here are the 3 arrays, A, B, and C. And the idea is, can you find one number from here, one number from here, one number from here? You add them up, you get 0. I don't know what the answer is on this example. I just made it up.
The answer is yes. 15 minus 5 and minus 10.
15 minus 5.
No, 15.
15 minus 5 minus 10. OK, so the answer is yes. Good.
Also minus 9, 8, and 1.
Lots of answers. OK. We need an algorithm to solve this idea. And here's an algorithm that I think I have heard some of you come up with. And it goes something like this. Instead of trying to, well, let's think of some brute force algorithms. One brute force algorithm is, let's take all the possibilities from here, all the possibilities from here, and all the possibilities from here, and see if any of them equals 0. How many possibilities would there be if there were n in each list? There's n choices here, n choices here, n choices here, so you get n cubed. OK? That's an exam level question. Everybody should be able to come up with an n cubed algorithm that solves this problem. OK? So we start from there. We're going to work our way down. So here's the next best step. The next best step is you think about it for a while and you think, OK, I got to do a little better. Here's what I'm going to do. I'm going to identify 2 of these, put them over here, and think of this one as separate. And I want to find out, is there any way for me to get 1 from here and 1 from here that add up to something in this column? The same problem, just a different way to think about it. But this way kind of leads you to think of a different idea. And here's an idea that I've heard people do. They say, OK, I'm going to add up all the n-squared possibilities here and just put them in a big list. So I've got all the n-squared possibilities. And now the problem is, can we find one of these numbers in that list that's n squared long? Everyone understand?
You want the negative of the last column.
The negative of the last column, right. Good. How do we do that? We got a list. It's got n squared elements in it. We have another list with n elements, and we want to search for an element in our list of n squared elements. Well, one thing is we could sort that list of n squared elements. That takes n squared log n squared, which is n squared log n. Log n squared is 2 log n. So it's n squared log n so far, big theta. That's to sort the list of all the possible combinations. And now, one by one, I'm done with this. This step is over. Next step. One by one, I'm going to take each of these numbers and search for it in this list. How long does that take to search for one of these numbers in a sorted list? Use binary search. So it's the log of the length of this list. That means log of n squared, which is 2 log n, which is big theta log n. So every one of these searches is going to take me big theta log n. There's n of these searches. So that takes me another n log n altogether. Okay? This is a solution that I've heard. Is this the solution that everyone who's solved it so far has come up with more or less? Yep. Give or take an isomorphism? Todd?
Sort the n squared?
So that you can do binary search on it. I guess we don't even need to. I mean, why bother? Just do the search in linear time, and this ends up being n squared. And we've already used up n squared log n, so why bother sorting?
Unless somehow when you got to positive numbers, you decided to give up because you had already gone by all the... You might be able to speed it up.
Maybe, but I agree. Todd's got a good point. This sorting of it just cuts it down to n log n. This step would have been n squared without the sorting, and we're already up to n squared log n, so why bother? Agreed. But our goal is to do better than n squared log n, because I mentioned in the problem set, or if I didn't, I should have mentioned, that you should try to do your best, and your best should be, no, you should really try to do your best, and even getting this far is plenty good on this problem, and is worth full credit. But there is a way to do it in n squared. And it's not a peculiar twisted sister way with an extra heap and amortizing it over this, and maybe one day if the constants are good and the moon is shining bright, it's going to be better. It's really better, it's really faster, and it's not complicated. You just have to think of it. Well, I forgot. No.
Is n squared plus n, that's still n squared, right?
Yes. Yeah. Do you have an idea, Seth?
Well, what if you took the 2 to the raise, added up all the possible combinations to see what all the possible combinations are, and then compare that against the 3rd array, see if any of those numbers are there?
So how does that comparing take? We've done n squared operations to do the additions, and then we have to find one of these numbers in that list of n squared. So the slow way to do that is to take a linear search, which would take n squared for each search. Oh, no, so Todd, no. It would take n squared to do the searching here, right?
You have to go through every possible...
Right, and then there's n of those, Seth, so there would be n cubed altogether to do it that way.
But you can pull it out and log in by binary search.
By binary search, you can knock it down to n squared log n. So this is not n log n, it's n squared log n also. So I'm losing the thread here. What? N squared to come up with these numbers. They're just a random list, right? And now each of these needs to be searched for in this list. The fastest you could do that is the log of this list, is log n. Log n squared, which is log n. That's if you sorted it. If you sort it, it's going to take n squared log n. If you don't sort it, it's going to take n squared to look through this list. And you have to do that n times. So you get n squared times n. And it gets n cubed. Do you get it, Rob?
Yep.
Yeah? Seth? Okay. Yeah?
Would it be worth doing a positive-negative check and then discarding all combinations which were either all positive or all negative?
I'm not sure, but my guess is that that might cut out like a 50% kind of a thing. I'm not sure that would help in general. I'd have to figure out more specifically how to do that.
It would cut out 1/3 of them.
A third of them, or some fraction. But I don't think it's going to knock it's not going to knock that log n off. All right, here's an idea. And I think once you see this idea, you're going to think, oh, that's a good idea. It's an idea that you can miss for a month and then just see it. And it's an idea somebody else can come up with on the spot. It's just kind of cool. The first thing we'll do, and I'll motivate this as we go along, is take each of these lists that we're normally adding together and making n squared. Let's not add them up and do the n squareds just yet. Let's first sort each list. Okay, that cost us n log n. That's less than n squared. So we can just do that for free So let's list them in order. Let's do this one first. I get minus 12 minus 9, 3, 6, 15. Thanks. And let's list the other one. I'm going to list the other one along this way so we can do the adding in a big table. And I got,
Minus 5, 2, 8, 13.
I'm going to list these backwards because it'll help us. Minus 5, 2, 8, 13, 17. And now let's look at this. I think to appreciate this algorithm, if you don't already see where we're going, you should actually just do it once, and we'll do it once now. It'll take 3 minutes, but we'll do it. Let's do all the additions and fill up this table. This is that n squared step we did before. But what happened before was we either searched through this whole n squared area. That took too long because it was n cubed for each of the n's. Or we sorted it. And in sorting it, we got it down to n squared log n. But it turns out that in this example, sorting it is helpful, but if you actually leave it less structured, you get more help. We're better off not sorting this when we get the n squared values. We're better off leaving it in a slightly less structured way, and we can leverage more information. And that is very, very unintuitive. And it's something you should keep in your repertoire when you're coming up with algorithms, that sometimes less is really more. And here's a great example of that. So let's go ahead and add. Those of you who are fast at adding, help me.
5, 8, 20, 23, 32.
And those of you who are not as fast can help me.
4, 16, 19, 28. Minus 4, minus 1, 11, 14, 23.
I can almost write as fast.
Minus 10, minus 7, 5, 8, 17. And I can't see the number.
Minus 17, minus...
Minus 14, minus 2, 1.
10. Did I make any mistakes? I don't think so. Now, what do you notice about this two-dimensional array? How is it structured? It's kind of obvious, but how is it structured?
The diagonals from northwest to southeast are more or less the same.
Whoa. All right.
If I want to check for minus 1, I would go down some of the diagonals from northwest to southeast.
Okay. I'm looking for something much simpler.
A bunch of negatives on the southwest.
In this direction, it gets bigger, and in this direction, right, so it gets bigger this way and this way. Fine. So what? This is the key thing. If you structure your two-dimensional array like this, you got a better thing than sorting. And the idea here is really similar to what you do when you merge things. And you'll see this idea in a minute. Now we are looking for the number. Let's put some in that actually takes a little work. Let's look for the number 15.
Minus 15 you want.
Minus 15. Right, because we want to make it obvious. So is it in there?
Nope. No.
Let's look for something that's actually in there.
Let's go on to
Minus 10.
10.
No, positive 10 you'd need.
You got 10 and minus 10.
Minus 10, yes. And you put the plus.
All right, let's make something up. Here, minus 19's in the thing. We're looking for 19. Okay? I want something out there so you can see how we find these things. We're going to search this two-dimensional array for 19. It's slow to go through the whole thing. That's too slow. That's an n-cubed algorithm. It's slow to sort it and do binary search. That's n squared log n. So what's a way to get through and find things in this structure and making sure that you do at most n steps for every number? That will give you n times n, which is n squared. Let's start. Where do you want to start?
Go to a column.
Let's start here.
You want to go to the southwest or to the southwest.
We're looking for 19, right? 19's bigger than 5. So where is it? To the right or down? Right. What about all of these? You never, ever look at them. 19 bigger than 8? Right or down? You either go right or you go down. Sooner or later, you go off the edge. We win. What's the worst case? The worst case is every move 1 to the right. 2n is the worst case. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. The worst you can do is twice the length of this list. It's not genius stuff. It's just really leveraging what you have to the best of your advantage. This would not take a long time to implement. This would be very efficient to implement. You would notice a big difference between this n squared idea and the binary search n squared log n idea. This is really what algorithms is all about, because this is just like the easiest kind of problem you can think of. It's just numbers and finding them in another set. It's not a graph thing. It's not a fancy data structure. All right, so that's really what the goal of this class is. It's to develop techniques and intuitions deep inside you so you take that second look at a problem that you think couldn't possibly be done any better. All right. The reason I think of it as emerging idea is because I don't actually, when I implement this, create this array. I just put these values next to each other in opposite order, and I keep a little pointer to this one and a little pointer to the other one, and I add them together as I go, and if my number is bigger, I go down one in this column, and if my number is smaller, I go down one in the other column. That's a lot like merging. Everybody see that idea? So I think of this as a merge algorithm. It's easier to see it when I make this picture, and easier for me to argue it. But it's really just two lists with two indices as fast as you could possibly be. You don't actually create a two-dimensional array. You don't even have the space. You don't even need it.
So you don't save your values?
No.
So if you want to search again, though, that would you'd have to do all that work again.
You'd have to do the addition again, but yeah. Well, the truth is, though, if you were doing lots of searches, it probably is better to do this. If you're doing, yes, I think that's a good point. Questions about this?
Doing at least n searches.
Right, because it would double the.
You're doing, well, no, because you're searching for all of these numbers, so each time you do it, you have to.
Oh, you mean we're doing at least n searches? Right, right, true. Yeah, so maybe it's, I don't know. I'm not sure which is better, to actually store them explicitly or to calculate them as you go. For n searches, it's probably pretty close. For n squared searches, it's probably better to print them out. All right. Everybody get it? Yeah, Todd?
If you had arranged your vector C,
Mm-hmm.
would you then be able to reuse some of the calculations you had kept locally?
My,
Like, if you know that the smallest number is minus 19, you'll know how far you need to get down to the south.
you mean if I had sorted this to begin with, you mean?
Then you know how far you need to get to the southwest of this
Then you could eliminate all the ones.
two-dimensional array that you never actually create, but you'd be able to remember some locally.
I don't know. My intuition is that I doubt I could leverage that. I don't think I can. If I could, I don't think I can get the whole thing under n squared using that. But maybe some constant factors I might be able to do. Yeah.
That might work if you started in a different corner, maybe. Like with the highest and lowest.
Or maybe deciding which corner to start in based on what the number is, perhaps. Yeah. Whenever you think of these engineering ideas, here's almost always the case. Practically, sometimes they work. And theoretically, you can always come up with a pathological example that makes the engineering idea look bad. So like you're saying, you'll decide which corner to stop at. I can probably weight these numbers in such a way that you'll think it's better to start there, but really it's better to start there. And finding those counterexamples is a worthwhile exercise, because it helps you be critical with your own algorithms. All right, so isn't this cool? Yeah? Jeff did some, here's the other cool thing before we get started on the main topic. Jeff did some cool testing on the sorting that I wanted to just report. And how big were the arrays? 50,000 we were looking at? 50,000 size arrays, and the largest number was 20,000, right? So the biggest was 20,000, and the size of the arrays was 50,000. And he ran it on insertion sort, right? Insertion sort was, what, about 100? How many seconds? 170 seconds. Quick sort was 2.5. Merge sort was like 3.5, 3.4 seconds. Heap sort was a little bigger, I thought. Well, I'll make it 4. I thought it was a little bigger. So pretty close, but quick sort beats it. And this is kind of fun. Jeff's got a little sort driving tester. It's kind of cool to play with. But the neat thing is, since he was only using numbers that were up to 20,000, I suggested that he throw counting sort in. And he was mildly hesitant, but since I was standing right next to him, and he felt obliged. So we wrote counting sort in about 5 minutes or so, and then threw it in his driver and ran that. And you can do counting sort on this because it's only an array of size 20,000, and at least nowadays, arrays of size 20,000 don't kill your machine. When I was doing this, 20K in an array was big for your RAM, but it's not anymore. So you can do counting sort. And counting sort, remember, is pretty fast. It's time proportional to this plus this. So counting sort, this was like, I forget, it was really fast. 0.6. Incredibly fast. Now, a lot of the sorts you do use values that are fixed less than 20,000. Almost, I mean, plenty don't, but a lot of them do. And everybody, so oh, quicksort, quicksort, quicksort. Well, this is fine, right? This is really good. And we have to go pretty high on the number here to slow down counting sort. We did put in 999,999,999 just to slow it down. And then it went to, I don't know, 100 or something, right? It was very slow.
Wait, what's the constraint? It has to be...
The constraint in counting sort is that you have to have a fixed highest number.
I thought it was proportional to the length of it was fixed and proportional to the length of the list.
If you did that, it's still linear.
Okay.
But anytime it's fixed, you can use it. So the complexity is always going to be the length of the list plus the highest number in the list. What we try to do with bucket sort and radix sort is leverage this idea even when we don't have a fixed value. So if the values are evenly distributed, we just make our own little buckets for bucket sort. And if you have a fixed number of digits, we just do it with radix sort and try to do it in phases. So we try to leverage this idea, but you can see why. This idea, as simple as it seems when you first hear it, making piles on your desk and collecting your piles, it really works, and it's good. And you should use it in the circumstances that it works. And you shouldn't just go ahead and use whatever sort Unix has given you, because you can probably do better if you know the particular application that you're using it for.
What method was sorting the buckets once they were created?
Oh, well, in counting sort,
But in the implementation you guys did, how did you sort them?
all you do is go through the counting array, and if you get up to, say, slot 3, and that has the number 9 in it, then a loop from 1 to 9, you copy 3 into the next spaces in the array that you were sorting it. In other words, there's no linked list in counting sort.
Oh, right.
Right? Right. With linked list, it would slow down a little bit, but you only need the linked list in radix sort or bucket sort. So you don't have that overhead. You just have a loop that runs through.
But if you had required it to be a stable sort, you'd have to build up a structure that actually remembered something other than how many times you hit 9.
Right. Right. Right.
You were sorting integers, but you were sorting...
If you were sorting records, you'd have to do something a little bit more, and maybe that constant factor would make this look worse. But my guess is it would still be faster than quicksort. I don't think that's such horrible overhead to run through a linked list and copy them down.
And all the counting sort is requiring that these not just be restricted by upper range of 20,000, but they all be integer values.
Yes.
All the other sorts can work with the same count of numbers, and they don't care.
And they could have float value. Absolutely.
Compared in.
Absolutely. But if the values are evenly distributed, then we can make 20,000 ranges of them and use bucket sort. And take these float values and just put them in the right bucket, but that would require the linked list structure for each bucket.
Like your n cubed n squared problem, those were real numbers, but ultimately it made no difference.
Made no difference, right. Other questions? We were talking last time about red-black trees, and I'm going to get back and we're going to finish that topic today. I'm going to talk in detail about how, number one, to delete nodes from a regular binary search tree, and then how to insert nodes into a red-black tree. I'm not going to spend the day talking about how to delete nodes from a red-black tree because it's more of the same kind of thing. It's much more hairy than inserting, and you won't get much out of it. And it's right there in the book if you do need and have to look at it, and you probably won't. So you'll get as much as you need from the stuff on inserting. So let's begin, first of all, with looking at a regular binary search tree that does not have to necessarily be broad and bushy, but can be scrawny and skinny, and figure out how we do inserting and deleting. Inserting will be easy. Deleting requires a little bit of work. And then we'll work on holding on to our cups so they don't fall down. All right, here we go. You okay? You spill that? Oh, that's not a binary search tree. going on? This is a 16. Okay. Here's a binary search tree. Recall that the right subtree has to be greater than the root, and the left subtree has to have values that are smaller than the root. Here's the root at the top. Searching for something in a binary search tree is binary search. You compare to the root, and then you look left or right, depending on the answer. Inserting something into a binary search tree is just like searching for it, but sooner or later you don't find it, and you end up at a nil, and at that nil, you insert your new node. The code for all this stuff is done in detail in the book. If you are having, fits over the book's notation, the book really models the C language for the most part. And I have a particular easy time understanding the book's code. So feel free to ask me, and I'll be happy to do a little, on-the-spot tutorial just to help you through reading the code. You'll get used to it, and it isn't so bad, and I can help you. In any case, the code is there. It goes left, right. Let's say we're inserting the number 17. We go right here. We go left here. We go left here. We go right here. You get a nil, and 17 would go in here. Okay, nothing complicated about that, except, of course, if you keep doing insertions, this can get unbalanced, and that's why we have red-black trees and variations of them. How do you delete from a tree? How do you delete from a tree? Let's do some easy ones. I want to delete this number 30 from a tree. I go down here, I find 30. 30 is a leaf. It's got nothing but nil children. Okay? Childless. Living alone. Sad. We snip them off. Bye-bye. It's easy to snip off the last one that has leaves. Fine. What about deleting 10? This is the second easiest thing. 10 has one child.
Do we like its child? Screwed it up.
We save the only child, and we send the parent away. Snip. We splice it out. We take this pointer and we move it around to the left of the left. The code is one line. So if it has one child, it's easy to splice it out. If it has no children, you just cut it off. What if it has two children? Then we have to think. And it doesn't take too much to figure this out, but it does require at least a little bit of concern, because deleting, say, 18 gives us trouble. We can't just splice it off. How come we can't just splice it off? Because we've got two children here.
You can move on, you can only move one.
Yeah.
If you find the greater element, replace it, it causes a recursive delete.
Would it necessarily be the greater element on this tree?
Well,
Let's slow up. There's something there, but let's slow up a little bit. If I just sliced off 18, then what do I do with its two children?
One of them's going to have to be a parent of the other.
Right? In the society of trees, every node can only have two children, no three children. So you can't just slice it off and send these two children foster care up to 20 because it's got three children, you're stuck. So you got to somehow fix things. So here's the trick. We're really good at deleting leaves, right? What we're going to try to do is get rid of 18 by finding a leaf that can take its place. Everyone understand? Now, what leaf could take its place? What leaf could possibly fit in here? 19 could fit in there. What is it in general? What leaf could take the place of 25? Is it always the one to the right?
That's the best. Chance.
No, it wouldn't be.
Yeah, it's always got to be the one.
What about this? What if I'm deleting 20? I can't put 25 up there because I got the same problem. I got to take a leaf. Which leaf do I put in here in place of 20?
The last child of the one all the way on the right.
The 30?
Yeah, go down, take
But if I put the 30 there, then it's not a binary search tree anymore, right, Joe? Because 25 is smaller. So I can't do that, but it's something like that. 21. That works. The 22, does 22 work?
No, it's going to be either leftmost leaf of the right branch or the rightmost leaf of the left branch?
Let me suggest one way that will just be, I think, dirt clear. No more baloney tree. Now you got dirt clear. I didn't mean that. I meant, well, crystal. Clear as mud, yeah. The number that you'd like to take the place here is the next number in the sorted order. Right? That's the best one to take the place, because that won't mess up anything. If everything to the right here is bigger than 20, and everything here to the left is smaller than 20, then if you just stuck the next number in sorted order in place of 20, you'd be all right. How do we know that the next one in sorted order happens to be sitting on a leaf? How do you get the next one in sorted order? Remember how you get a sorted order for a tree? You do what kind of traversal? You do left, then root, then right. It's called an in-order traversal. So, after you've done the left subtree, and after you've done here, now you're going to keep going in your in-order traversal and traverse this right part. What's the first piece of this right subtree that's going to be counted? It's going to be the leftmost leaf because of the recursion. Now in the book they show you code that takes any node and finds the leftmost leaf of the right subtree. You could also just do the in-order traversal yourself and keep a list of the pointers and know which one comes next. There's lots of ways to do it. But it's not too tough to find the successor of this node, the one that comes next in alphabetical order or numerical order. And what you do is you change 20 to 21 and you slice that off.
Or the immediate predecessor to 20.
It happens to work here, yes. I'm not...
You could always do it with 19 as well as 21.
19 is
Oh, you could always do it that way, yes, yes. But the standard way is to do the successor rather than the predecessor. Absolutely, you could do the predecessor too. Absolutely. It's symmetric. Okay, questions about this? So what Sam was saying, and I think Chris said this a few moments ago, you can either get the leftmost leaf of the right side or the rightmost leaf of the left side. And those are the predecessor and successor respectively, successor and predecessor respectively of this one. And they're both leaves, so you can replace it. All right. Let me fix this a little. Let's say the next thing I add is 23. Make sure everybody gets this. And now I want to delete 21. Okay, there's always a little twist to all these things that I make seem so straightforward. If we go through our method, this is the next one that gets counted, right? This is the leftmost of the right side. This is the one that we want to put up there. It'd be just fine. You can put 22 up there. It does keep everything in binary search tree fashion. That's okay. But it's not a leaf. So I lied. It's not always a leaf. But it never has a left child. It has at most one child. So you have to be careful when you're coding this, not just to splice it off, but sometimes if it has a child, you have to go connect this child to the side. So you have to splice it out, not just cut it off all the time. Joe, you have a question?
If let's say 21, before you cut off and put it up, had children, you would just continue down the left branch to the children of, let's say 21 had a child of 20.
Then we wouldn't be replacing...
I understand.
Right.
I understand 20 is up there, but is that what you would just continue going down the left branch all the way down to...
To the leftmost before you'd make the switch. Right. Right. You wouldn't stop earlier if it had a left child. You keep going down because none of those would be the successor of these. The successor is the leftmost one all the way at the end.
After the first right.
Make a right turn and then go all the way to the left. Right. Right. It's like directions in the Middle East. Straight, straight, straight.
So you'll never have to do a recursive delete because it'll always have just one child, so you can always just connect the pointer. Is that
exactly?
Reliable?
You don't have to go delete and then delete again and then delete again. That's true. That's true. And you can avoid it.
From having more than one child. I mean, if we wanted to add 24 now, it would be 22 and then 23 and then 24, and now it's got more than one child, which breaks that stipulation. You said it can only have
More than one descendant.
The one that you're switching it with, the 22 that you're switching up here, can have at most one child.
Oh, but you're not counting the 24 as a child.
No, that's a grandchild. Right. No, seriously. So the only problem is when something has two children. Then you can't splice it out. When it has one child or zero, you can splice it out. So the key thing is here that we can always splice out the one that we really want to switch here and go ahead and do that. So you switch a data value and you change a pointer. Two operations. All right. There was a little searching to find it, but that's about log n time. The deletions are a little trickier, and that's why I'm not going to do them. But the insertions will give you enough of a feeling of how to manipulate a red-black tree. Okay, questions about this? Okay, Chris, good? Okay. I brought my lucky pen. I'm going to give this to you, Joe. This is a special pen. It's got red on one side. It's got blue on the other side. If you insert things into a red-black tree with this pen and you try to color the node the wrong color, the ink won't come out. It's guaranteed. It's for Sunday's exam. It's all yours. All right. Here we go. We're going to do a couple examples and then talk about the idea in general. And I could use some nice red. Red, black, black, red. You can't see the numbers anymore.
Why'd you draw the circles in red? Write the numbers.
The numbers.
Very clever.
You got to wonder. There we go. Now everyone's happy. This is a binary search tree. It's also a red-black tree. All the leaves are the nils, and you don't see them, but they're all black. Okay, there's 1, 2, 3, 4, 5 nils. They're all black. Okay? Every node is either red or black. The height from any tree, from any node down to the bottom, has the same number of black nodes. So the black height of any node is the same no matter what path you take. Starting from here, it's 1, 2. Starting from here, it's 1, 2. Starting from here, it's 1. Starting from here, it's 1. No matter what node you start with, same distance. Every red node has black children, 2 black children. Black nodes can have anything you want. Okay.
So any number of black children, right? It just has to have black children.
Right. It can have one, but it can't have red. Right. All right. So this is a red-black tree, and now we're going to insert something into it and see if we can fix it. How bad can it get? If we put a new number in, let's say we're going to put 70 in. 70 goes here in the binary search tree. If we insert the value and make it red, then we minimize the number of bad things that can happen. Well, for one thing, at least it's red or black. For another thing, the children are still, the nils are still all black. For another thing, the distances haven't changed because we haven't introduced any new black ones. The only thing that can go wrong is that if you had a red one here, now you've got a red parent of a red child. Everybody with me? That's the only thing that goes wrong with red-black insertion. And that's what we have to fix. And there are a number of different cases. The code in the book makes it seem like there's 6 or 7 different cases. There's really 3 cases. The reason there are 6 in the book is because they have symmetrical cases when you're on the right side and when you're on the left side. But there's really 3 different things that can happen. And this is one case. How would you fix this? I want you to develop intuition before I just give you a bunch of rules. How would you fix this red-red? What do you want to do?
Move the red from 60 to 50 first. And then switch the red and the black.
Swap these two. Leave this red. Change this to black. So this becomes a black node, and this becomes a red node. It's okay. We fixed this problem.
But the path from 40 on down doesn't have an equal number of black seeds, right?
No?
So you got
Yeah,
red,
it
red,
is a red child.
No, it does have the same number of blacks. We haven't changed the black path, have we?
40, 50.
This is red.
Right, so you got red, red.
We have a red-red, that problem, but we don't have a black distance problem. It's still 1, 2, 1, 2, 1, 2, any way down from any of these, from the root node. We haven't added any black nodes anywhere, so we haven't changed the distance anyplace. So that's okay. So this idea is actually okay, and what we've done is we've shifted our problem up 2 levels.
Don't we have an additional path, 40, 50, down to the left to a nil? 40, 50 to the nil? 50 has only one child.
Oh, you're right, Sam. I'm wrong. You're right. This has 1 and this has 2. You're right. You're right. So this is bad. You're right. And we have this 40-50 problem. So this doesn't work. We need a better idea. All right. Ugh.
In fact, we can't solve it. No, you said that
We have to mutate this tree.
one path can't be more than twice as long as another path.
But we'll have to mutate the tree. We'll have to cut it apart. Before I show you how to mutate this tree, I want to show you the easy case. This is actually a hard case. And you know why it's a hard case?
This is red.
No, because you see this guy over here? There's a black one there. When we switch this red and black, we do get this distance problem. I was wrong that there's no distance problem. There really is. When we switch this and make this red and make this black, and this guy was a black one?
You started out with a distance problem.
No, we didn't. This is not a distance problem. 1, 2, 1, 2, 1, 2. Everything's 2 from the root. It's okay. But if we go ahead and switch these 2 colors in order to shift up our red-red clash, we will get a distance problem because going down this way we'll get 1 and going down the other ways we'll get 2. Here's a case where that wouldn't happen. Let's say we happen to have a red node out over here that was 45. Let's say we did. This is the easy case. The easy case is you get a clash and the uncle of the new one, the uncle, the first cousin, this one, uncle of this one, the uncle of this one is red. If the uncle of this one is red, then we can take this red and this black and try to switch them and see what happens. Just do a color switch. Let's see what happens. This changes to red, and this changes to black. Is it any better?
You did change to 45.
Well, now we have a 45-50 problem and a 40-50 problem. Among other things.
Can we do it a better way? I'll show you how to do this, but I want you to discover it because it's worthwhile. You'll remember it better. What number was here? 50? Now I forgot. 50 and red 60. What should we do? The easy case is when this is red. What should we do?
Well, change 45.
Sorry, you're adding 70 to this?
We're adding 70 and we got a clash.
Okay, and you have 6 now, so you should be able to resolve it.
We're just going to change colors. It's not a tough resolution. Everybody's just having...
60 change to black, 50 changes to red, and 40 changes to black.
Well, hold off on the top one, but let's just change this locally first. If we have these two being the same color red, then we can fix this clash by changing this to a black, changing this to a red, and changing this to a black. If there's a black here to begin with, we can't do that because it's already black, and we can't put another black in there to even out the distances. But if it's red to begin with, we can do it like this. Watch.
Is it necessary to change 50 to...
Yeah, to keep it equal with the other side.
Oh yeah, with the
So
30.
we're going to do this. This is going to turn black, this is going to turn black, and this is going to turn red. And now let's look at it. The distances are still okay because we've added in that extra black on this side to take the slack up. The red-red clash is gone. And what have we done with it? Instead of it being here and here, now it's here and here. It's moved up 2 generations. This is the easy case of fixing an insertion to a red-black tree. The easy case is when the uncle of the thing you just inserted is red. Then you can change the 2 brothers to black, the parent to red, and you have shifted the red-red clash up 2 generations.
Now you have to change the top to...
Now we're going to repeat the issue. But now look at the uncle. The clash is here. There's no uncle. Right, right. At this point, there's an easy ending. But I'm going to hold off on this ending. I want you to see just the first basic case of how to move it up 2 generations. The basic loop goes like this. Start at the bottom. If you get the easy case, do the recoloring and move it up 2 generations, and repeat doing that. Keep moving it up 2 generations until you get kind of toward the top. If you ever get a situation where the uncle isn't red, then you got to do something different. Then you've got to mutate the tree. You got to chop it up and reconnect it. Now that's where things get a little bit complicated, and you have to be able to know how to mutate a binary search tree without losing its searching property and without losing its red-black property. And at this point, if you were creating red-black trees from scratch, you might just give up because it seems like it's just so hopeless to come up with a consistent way of chopping up a tree and reconnecting it. You might get it to work in a particular example, but you might not get it to work in general. The methods I'm going to show you right now work in general. And they're based on a tool called rotations. And they are basically mutations of a binary search tree that keep the binary search structure. So you need to know about a rotation because what we're going to do when the uncle is black is we're going to do a particular kind of rotation. Sometimes we're going to do 2 rotations, sometimes we're going to do 1. Here's the good news. In the easy case, we move it up 2 generations. In the hard case, I said we have to do rotations and mutate. If you ever have to do a rotation and mutate, then you're finished and you never have to continue any further up the tree. So the worst thing that happens is you recolor moving up the tree, and at some point you have to do a couple of rotations, and then you're done. If you actually move all the way up the tree without having the bad case, you just recolor all the way up. Now rotations take a constant number of pointer movements. So the worst case for all this insertion and fixing the tree is going to be proportional to the height of the tree, which in a red-black tree is log n. So that's where we're headed. I have to show you now how to take care of the hard cases and what these rotations are.
Is that the only easy case, is the red uncle situation?
Yes. The black uncle always requires a rotation.
The red uncle, the crossing or whatever it is, then is red. It has to be red.
Well, if you have a clash, this is always red. The brother's always red.
Yeah, but in 70 was black.
If this was black?
No, 70.
Oh, if this was black, well, this will never be black because we always add in a red node. And the reason we do that, Gador, is because if we added in a black node, it would mess up a much harder property to fix, the distance property. So we always add the red node to make sure that the worst thing that happens is the color clash. But you're right, if it were black, then we'd have different cases. But it's never black. It's okay.
And if the grandparent was already red and 50 was... already red, then it would have to have black. Never mind. Gotcha.
I'm not sure everybody gets that, but that's a really excellent question.
If 50 was already red, if the grandparent was already red, then this case would be impossible because both of his children would have to be black.
Right.
So the uncle and the father.
Right. Chris is asking what happens when you can't change this from black to red because it's already red. And then he answered his own question, like he often does, and said that, oh, but that can't happen because if this were already red, then by the red-black property, the two children would have to have been black, and then we wouldn't have had a clash to begin with. That's a very mathematical argument that relates directly to coding this. You don't have that case to worry about, so you leave it out of your code. And it's a really important thing to notice. Yeah, Tony.
When you say rotations happen in constant pointer time, and they correspond to log n being the height of the tree, are you saying that you only have rotations of 3 elements and you ascend vertically along whatever chain is the parent chain, and so you're only going to be dealing with the children of each of those parents as you go up the chain?
I'm saying that when you do a rotation, you snip 2 or 3 pointers, you reconnect 2 or 3 pointers, and you're done.
So that's
and it doesn't propagate its way up. AVL trees, by the way, used to propagate. The reason these take the place of AVL trees is because there, when you fix them and you need a rotation, it might propagate up and need another rotation. Instead of just recoloring on the way up, you might have had to rotate all the way on the way up. But in red-black trees, when you're ready to rotate, that's the end. It's a little bit more efficient constant-wise, not asymptotically.
Don't you normally keep the root colored black always?
You mean me?
Or
Does one? Yeah. Heather's made a very good point. And here's a question that could be a short answer question on an exam. If you take a red-black tree and the root's red, and I change the root to black, is it still a red-black tree? Yes. Because it doesn't change any of the black distances. Well, it changes them all by making one more. So it doesn't make them unequal.
But black can be parent to anybody.
Black can be parent to anybody. Absolutely. And the general assumption is that when you're done fixing a red-black tree, you always recolor the top black because it gives you more flexibility. That's true. Why did I do it this way? No reason. It doesn't hurt to do it. Nothing wrong doing it this way. But you're right. For convenience, we tend to make it black. This is a little snapshot of the middle of a tree. You're coming down here. There's a big tree on top somewhere. It goes up, goes around. It's got this little piece in the middle. This node is indicated by a square and this one by a circle just so that you can identify the two. And then subtrees underneath called A, B, and C that also continue going down. We are going to mutate this whole tree by chopping these things up and reconnecting them in the appropriate way. And here's what it looks like. This is a right rotation. A right rotation takes the circle and the square and turns them to the right. Like this. What used to go into the square now goes into the circle. The square's left used to go to a circle. Now the circle's right goes to the square. And now the issue is, how do we reconnect the A, B's, and C's? So think of this just like a rotation. That's why they're called rotations. Imagine that you took this and turned it like that. The C would still be where? Over here. Leave it there. What about the rest? The A still comes off the circle. And now the thing is, what happened to that stupid B? The B should come right out here. But it can't because it's a binary search tree. So the B gets snipped and reconnected here. This is a rotation mutating the tree into this. Why is this useful and what is it for? I mean, so what? I changed the tree around a little bit. Here's the thing you should notice. Things have changed in this tree. The locations of the nodes, the relationships between them have changed. They've changed in such a way that I can probably leverage this to help me fix my red-black issues over here, because I move my nodes around. But the key thing about these rotations is not that just they can be beneficial for fixing red-black, but that they do not affect the ordering of the binary search tree. I want to convince you of that because it's easy to convince you of that. Let's say we want to do a traversal of this tree and see what the sorted order would be. Okay, what would it be? We'd come down here sooner or later, and we would do the left side first, and then the square, and then the right side. Doing here, we do the left side first, A. Then we would do the circle. Then we do the B. Then we do the square, and then the C. Let's do the same traversal here, which indicates our left is smaller, and our right is bigger, and our middle is in between. We first do a left. It's A. Then we do the root, the circle. Then we do the right. In order to do the right, you do the left. It's B. The root is square, and the right is C. A circle B square C, A circle B square C. The ordering of this tree, with everything on top and everything below, is the same as the ordering on this tree. In other words, if this is a binary search tree, so is this a binary search tree. This is a general way to mutate a tree and not lose its binary search property. It is the ABCs of fiddling with a binary search tree. Everybody talks about right rotations and left rotations, not about particular lower levels than that. This is the unit of moving things around in a binary search tree. Chris, yeah, what's bugging you?
Why am I wrong? The circle's to the left of the square, that means it's less than the square, right?
Yes, and the square's to the right of the circle. That means the square is bigger than the circle.
Yeah, right.
Yeah.
Thanks.
Chris, watch those neurons fire.
Or not fire.
Questions about this? This is not so easy the first time you see it. It is subtle, but it's not so bad if you think about it for a while. Yeah, John.
Could we just take a little step back and a motivation about why red-black trees are so fantastically brilliant? But we want to do all this mutation and insertion and running around and stuff like that.
Yes.
Because it seems like you're simply distributing overhead, because if you left the binary search tree, you don't have any of this kind of malarkey when you're adding stuff. You simply may get longer searches. But with this stuff, you get shorter searches because you're doing all of this stuff when you insert. So, motivate us.
All right. The other team is better than us, but we've been working hard. Nobody expects us to win. You didn't expect yourselves to win, but you are going to go out there and give it your best, John West.
Okay.
All right, so let's go on to the other kind of rotation. All right, if you have a regular binary search tree and you just keep adding stuff to it, it really gets thin and scrawny. And then when you search, the search is going to take proportional to the number of elements in the tree instead of to the log of those elements. The difference between n and log n is huge. It's much more than the difference between, n and n log n. It's a really big factor. So it's true, we have all this overhead in our red-black trees, but it guarantees us that our height stays just 2 log n. And 2 log n is really small compared to n. And what's the payoff? All we have to do is fix it every time we do an insertion. When you do a regular binary search, it takes log n just to find the thing. And this fixing is taking just another log n. So we're trading a few factors of log n to get rid of a potential linear. That's like trading a few linear factors to get rid of an exponential. So it's a real worthwhile trade-off. It's not like that k log k, k log n trade-off. This really, really does work. This really is used. And it's an alternative to heaps. Well, it's the best I can do.
Well, if that's the case, why don't they just set a counter and say when you do 20 insertions, deletions, just recreate the whole tree, which has got to be faster than doing 20 mutations for every.
No, I don't think it is.
Because you already have
20 mutations altogether is going to be 20 log n. And if you recreate the tree every time, that's going to be 20 log n every time you recreate the tree. So I think it's better just to fix it as you go. I think it's better not to recreate it. If you recreate it every time, it's as if you...
No, I'm not saying recreate every time. Set a counter so that every 50 or every 20 things you do, then you recreate the tree.
Yeah, but recreating it is just going to be n fixes. You got to put them all in again. Creating it from scratch isn't so easy. You're going to see the first problem set that you'll start tomorrow is take these numbers and throw them into a red-black tree. And that's the best way to create it, is to actually insert them one by one. So in some sense, you know, saying, oh, we'll do it easier by creating it from scratch, it's not so easy to create it from scratch, because every time we add a new one, we do have to fix it. So creating it is this.
Talking about like just a regular binary tree. If you want to keep the distance proportional, right? You just do insertions into the tree.
Yeah.
And then, you know, assuming you know how large the tree is.
Yeah.
Okay.
Oh, so at some point you're going to make it bushy instead of skinny?
Right.
That's not obvious how to do. It's not obvious how to snip the tree apart and then make it bushy.
Yeah, what I'm saying is just recreate the whole tree by finding the median of the tree and just recreating it from that point. Then you know you're going to have a bushy tree every 50 insertion and deletions.
So but sorting is an n log n thing. You have to sort it in order to do that.
Right. In order to find, well, in order to get it ordered so that you knew all the ones, well, you'd have to at least partition it. You have to do at least a linear time thing.
And that differs from redoing the tree every time by a constant factor. So basically equivalent to redoing your tree every time you insert an element, which is not good, right?
And the point of this data structure is to give us a method to maintain a balanced tree.
Right. Right.
After recruiting.
Right. Right. All right. I think it's time to see a big example. I'm going to do a couple of them. One is very similar to one you can find in the book, and one is a little different because, as usual, the book will give you lots of good stuff, but there'll always be some special case that won't be completely included in the cases that they show. So,
are we done with rotations?
we're done with rotations, but I'm going to use them now. Questions? Anything so far? I think you need to see an example soon. Yeah, Donna.
What is the cost of that rotation?
It's 5 steps. You can see the code for it. It's if this isn't nil, then move this pointer here, and otherwise move this pointer there. It's a constant number of steps. Yeah.
You're saying it never creates red-black issues somehow?
Once you're ready to do a rotation, the whole tree is fixed. Once you finish, after you've done that rotation, the tree is fixed. Sometimes you need to do 2 rotations, sometimes 1. But once you've done both those rotations if necessary, you are done and your fixing is finished.
No matter how big the tree is.
No matter how high up it goes, right, right.
It seems like you're switching an element. You're changing the parent of an element, which seems like it could create a red-black issue, right? You're moving B from one parent to another parent, so if that...
We're also going to recolor so that the one here ends up being black.
Oh,
you'll see.
Add a third color. Okay.
Red, black, yellow trees. Red, black, yellow trees. I think I need to show you a big example, and then I will summarize the 3 cases on the side, rather than summarizing first. I think you need to see something really practical at this point. So let's write these out. 11, 2, 14, 15, 1, 7, 5, 8. Black, red, 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 red. Okay. All right, there's a red-black binary search tree. Let's check it to make sure I didn't goof. Looks okay, right? All the criterion are satisfied. We are now going to add the number 4. What we're going to see in this example is all 3 cases. The very first thing that's going to happen is the happy case, the easy case. And that will bump up our class 2 generations. Then we will see the bad case, where the uncle's black. In that situation, we have 2 possibilities. One requires a single rotation. One requires first a preparatory rotation and then a single rotation. And you'll see both those situations coming up. All right, so putting 4 in, it goes over here at the end. It's red. 4. I'm going to redraw this because I think it's the easiest way to see it. The uncle here is red. This is the easy case. And we said in the easy case, we make these two black, and we make this one red, thereby moving up our clash to 2 and 7. So I'm going to redraw this tree with that in mind. 11, 14, 15, 2, 1. 7's going to be red. 5, 8, 4. And one's black. That's what it looks like right now. As we've discussed before, when the uncle's red, this is perfect. It keeps the distances even, and it moves the red-red clash up 2 levels. And now we are ready to repeat. We're in the while loop. We're doing it all again. If this, where's the uncle here? Is it this one? Is it this one? Where's the uncle? This is the uncle. It's black, so we got trouble. Okay? If it weren't black, we could just pop it up and we'd be done. We'd move the colors up and we'd be finished. But it's black, so we have to do some shifting. There's 2 cases here, and this is the hardest part of doing the insertions. One case is when you're coming off from the right, and one case is when you're coming off from the left. This is the very worst case. This is the one that's going to require 2 rotations. It will, yeah?
It may not fit the algorithm, but when we swap the color on 14 and 15, then the uncle would be red, and we could just...
No, because then 15 has a single black left and has a double black right.
Your idea, Doug, is to swap these 2 colors now and just, and make this have a red uncle?
Right. But the height of the black trees from 15 down is not the same.
The height of the black tree from here down would have 2 in this direction and 1 in that direction. So you can't do that trick. But what Doug is thinking about is exactly what you should be thinking about if you were creating a data structure like this. I mean, you don't have to most of the time. You pick up what other people have done, but that won't work, unfortunately. Yeah, Tony?
Sorry, but what is the point of having nils if they don't count as black nodes?
They do count as black.
Okay, then shouldn't all these red ones, are we just assuming that the nils are there?
Yeah, they're there. There's blacks coming out here, blacks coming out here. Right. I'm not writing them in, but they're there. And they count. Right. So there's 2 possibilities here when the uncle's black. Either we're on the right side or we're on the left side. Okay? On the right side, when it goes like this, that's worse than when it goes like this. Here's what we're going to do.
What was that?
When it goes like this, we'd be better off if the red were over here. Then we could fix it with 1 rotation. Since the red's over here on the other side, it's going to have to take 2 rotations. When we're done with this first rotation, then it's going to actually be exactly the situation where the red's on the other side. So what happens if the red's on the wrong side is you do a preliminary rotation, set it up so that it's the better black uncle case. Okay? So in the black uncle case, either it's on this side or this side. If it's on the wrong side, do a rotation to put it on the right side, and then do a final rotation to fix it. If it's on the good side to begin with, just do a single rotation and fix it right there.
Where are we measuring from now? What's our protagonist whose uncle we're talking about?
7.
Okay.
7 has an uncle 14.
Okay.
And we're going to rotate this pair.
Why is the one better than the other?
Matter of politics. If you have the same uncle.
Because we'd really like to do a right rotation to fix this. And you can't do a right rotation when it's in this direction.
But you said right and left rotations are symmetrical.
Yeah,
Why are we...
That's why
Well,
I understand what...
when something is going to the right side, you can only rotate it left. But to really do the fixing, we're going to need to rotate around to the right.
When something's going to the left side, you can only do it left.
When something's pointing to the left side, you can rotate it to the right. When something's pointing to the right side, you can rotate it to the left.
Yeah, let's try to show us. And then we'll make a lot more sense.
Here we go. This 2 and this 7 are this circle and this square respectively. Okay? We are going to take that picture and turn it into this picture. 11, 14, 15, 7, 2. I want you guys to tell me. What's coming off the 7 when you rotate it? On the right side. 8 comes off the 7. What comes off the 2 on the left side? 1. And what comes off the 2 on the right side? This subtree. The 5, 4 subtree. That whole thing comes off. Everybody see the rotation? This is the trickiest thing I've done all day probably. So let's make sure everybody gets it. Put these lines in. I gotta color these with the right colors. Red. 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 That's the rotation. The step I just did is a rotation. Let's look at it again slowly. I took this 2 and 7, I rotated them around. The 7 held its 8, the 2 held its 1, and what used to be connected to the left side of the 7 got snipped off and got connected to the right side of the 2. I rotated it exactly in this way. I did it because now it's in a position that I can rotate it to the right and fix the whole tree and be finished. So if it's in the wrong direction, do a preliminary rotation, and now we're ready to fix it. And I'll show you the final rotation that fixes it. If we're in the right orientation, then we would have just done this final step. We wouldn't have done this preliminary step. So it's either 1 rotation or 2. Questions?
So do we not worry about recoloring now and wait until
We're going to recolor right now. And then we're going to rotate. The last step is a recolor and a rotate. This step is just a rotate. So it might have looked like this to begin with. What's the uncle here? It's the same uncle, right? It's the same thing. The whole point is that if it's in the wrong orientation, we just rotate it and get it in the right orientation.
It's a different nephew.
Yeah, 2 is not the nephew.
2's the problem, right? But the same uncle, right? You can't really mutate family lines this way. I don't want you as my brother. I want you as my nephew. I want my nephew as my brother. Ooh. If my brother ever sees this, then he'll really... Anyway. How do we fix this? We have to recolor it. What do you want to do?
Switch the colors of 7 and 11.
Good. Good. That's exactly right. What we're going to do right now is the last step. The first thing you do is recolor 7 and 11. Make this black and make this red. Now, is that good just by itself?
No.
Why not? Why not? Heather, how come? Why not? Because the height's off now. We're going to rotate it now and fix the height. So if it's in the right orientation, like it is now, we switch the color of the top one of the clash with the one that's on top of that. We swap them. It fixes the color switch, but we have to rotate to fix the distance that got messed up. Sharon, you had a question?
I just was wondering why we need to recolor before we rotate.
Oh, you can rotate and then recolor. It doesn't matter. I'm just...
Okay.
It doesn't matter what order you do it, as long as you do it when you're done.
So, could we skip the recoloring between the 2 rotations? Or
You can do rotate, rotate, recolor, or rotate, recolor, rotate, because you're going to have to do all 3.
okay.
As long as you do the first rotation before the rotate, recolor combination, it's okay. It doesn't matter. The only reason I recolored it is because somebody in class said, hey, do we recolor it now? And I go, well, if you're thinking along those lines, then let's recolor it. Let's rotate this to the right. It's this pair that's rotating.
We just did that. We were rotating around 711, right?
Right. Should have waited till I did it, huh? Right, we're going to rotate this pair. You're right. We want 7 to pop up to the middle because it's going to even out the distances. We have this extra black that we stuck in here, and that messed things up. We want to move it up to the top to even it out. What does it look like when we're done? 7, 11, 8, 14, 15, 2, 1, 5, 4. And here's the reds. A red here, a red here, a red here, and a red here. Let's check to see that that's right. The 7 and 11 rotate around. The 11 still holds its 14 and 15. The 7 still holds its 2, 1, 5, 4. And the right part of the 7 that's got no place to go gets snipped off and connected to the left part of the 11. So first we did a left rotation, and now we did a right rotation. Yes, Sam?
Draw the original. I think you managed to erase the original.
I just did, yes.
Could you draw?
I can draw it over here.
Yeah,
That's the original.
thank you.
Yes?
I see that it works, and that's great. But in what sense was the first position before the first rotation the wrong position that we somehow fixed after we did the rotation, the first one?
Here.
Yeah. How can you tell that that's not the better way for it to be?
Oh. If the uncle is on the right, here's the grandparent.
Yeah.
If the uncle is on the right side of the grandparent, and this is on the same side, also the right side, that's the wrong orientation. You want the uncle and the nephew to be on opposite sides. If one's on the right, the other should be on the left. If one's on the left, the other should be on the right. If they go in the same orientation, it's going to be wrong. Are you asking me how you actually decide, or why that's?
Well, I guess both.
So how you actually decide, you look at those orientations. Why? It's because if they're in the same orientation, there's no way to get this guy, which is what we want, around to the right. We want to shift it to the right here to even things out. And we can't do it when it's oriented this way. So we rotate it that way, and then we can orient it to the right. At least that's a fluffy way of explaining it. Because it works. That's the easy way to explain it. I mean, there are alternatives. I was surfing on the web last night, and I found some site on red-black trees published by some Japanese author that I had never heard of up until last night, and a big blurb by the person who had it on their website that said, this is the most elegant formulation of red-black trees I've ever seen, a little simpler than you'll see in CLR, which is our textbook. And I tried to look at it, but the code was in a language that was so obtuse, I said, ah. Now, here's the thing. Once you understand this, and you get really used to it, unless somebody convinces you that a new way is like particularly good, I'm just not that interested in it. So going from AVL trees to red-black trees, people are also a little resistant, but red-black trees are really better, and you can convince somebody of that. But I haven't really seen something that's particularly more elegant than this in implementing balanced binary search trees. And there may be alternatives, and that's really what you're asking about. Is this the only way? Maybe there's other rotations that would work. I mean,
No, that wasn't really what
you're just saying.
so advanced. I just couldn't quite see why this makes it. I mean, I can see in the example that it works, and I just couldn't see what.
Oh, why is it working in general? I'm going to show you now the cases in general, more abstractly, not in this example, and you'll see how the heights stay the same and how everything fits. As far as where we are, I think we're right on schedule with the syllabus, but I'd like to start talking about graph algorithms next time. So we're going to introduce a new data structure called graphs. We'll talk about algorithms on graphs, some real basic ones without any fancy issues to them, just real bottom level play around with graphs. And then we'll move over to more complicated algorithms with graphs and other data structures. And that'll take about 4 lectures. So right now I just want to finish this up and give you the general rules. Here's the rules for switching the insertions of a tree. Here's case 1. It looks like this. You have a black, you have a red, you have a red, and another red. This is the good case. You have a clash of a red. Okay, this is the middle of a tree somewhere. You have a clash of a red. Its uncle is a red. You fix this. How do you fix it? This turns into a red. These two turn to blacks. And this one stays red. Okay? Convince yourself that this keeps everything below this point a red-black tree. Okay, this is the only clash. The distances are all okay. When you turn it into here, the number of blacks from this point on are the same because whatever this one was taken up is counted once here and once here. So the distances stay the same. There's no more red-red clash. The only thing that could happen is that this red, as it moves upward, might clash again. But we have handled the tree completely from this local point of view, and we've moved the difficulty up 2 generations. Okay, that's the easy case. That's case 1. Okay, that's not fluffy, right? That's still fluffy? That shouldn't be fluffy. Okay. So let's look at the harder case. Spiky. Clear as mud, yes. All right, case 2. Black, red, black. Now, since this case is going to involve a rotation, I need to put a little more labels on the nodes. So I'll call this X, Y, Z, U. Okay, just so you know which one is which. This is a harder situation. You know what? I'll do it last because it's harder. I'm going to do case 2 last. I'll do case 3 here because it's easier.
Then that would be case 2.
Case.
Just kidding.
Yeah. Black, red, black. X. I'll call it Z, Y, U. This is the case of a black uncle. So it's not the easy case 1. But it's the good case of a black uncle because the direction here is opposite the one here. So we can go ahead and rotate it to the right. And that's what we're going to do. Let's change this. What's the whole thing going to look like after we've rotated it? Let's put little leaves here. I'll call these A, B, C, D, E. What's it all going to look like when I'm done? Do it yourselves once, otherwise you'll never do it. Let's rotating it around. So what's going to be here? What's going to be at the top? Z. And what color is it? We're going to change the color when we're done, right? So let's not color them yet. We'll just put Z there. We'll color them later. What goes here to the left of Z? Y. And under y is the same old AB subtrees. What about to the right of z?
X.
To the right of x is the u. D and E. What comes off the left of the x? The thing we called C. Now, how do we color all these? X is red, Z is black, Y is
Red. And everything else is as before.
Look at these two. If before we had the same distance from here down this way as we did this way, try to convince yourself that you still have the same distance as here. Let's look. From you down, things are the same. There's 1b on top of it on the right. There's 1b on top of it on the right here. Going to the left, here we had z and y, but they were both red. Here we only have y, but that's red. So whatever we had here with z and y is going to be the same as we have here with just y, so the distances will be the same. Not fluffy, just you can calculate it. You can really calculate the distance here and here relative to the distance here and here, and they're going to be the same as far as the black nodes go. There's no red-red clash here, as you can see. None of the things under here were affected at all or up here. And what's more, this has become black. So there can't possibly be a clash with anything higher up. Right? That's why we're done now. We got rid of the distance problem. We kept the distance issue under check. We got rid of the red clash. Sharon? Yeah.
Why does that mean there can't possibly be a clash further up if that top node is black?
Because if you put a black node in, it's the same reason that Heather said we could always make the root black. What could possibly be wrong with turning this black? If there's a black on top of it, there's no problem. If there's a red on top of it, there's no problem. The only thing that can make a problem is if you add a red node in, because that can clash with a red node on top of it.
Actually, adding a black can create a distance problem. So that's the question.
But we didn't add any extra blacks. This had one here and then one below it, and it has the same one on top and one below it. So, right, Chris is right, and maybe that was your point. That if you add a black, you can add a distance, but we didn't add any new ones, we just kept it the same. A little better? You think it's better to see this stuff before the example or the example before this? Or, I don't know. Example before this. I think so. But let's do this now. Last thing. I labeled this zy on purpose because case 2 is going to turn into case 3. Okay? The way we fix case 2 is the worst possible thing. It's got a black uncle, and the thing is in the wrong orientation. A, B, C, D, E. We're going to rotate the YZ combination here to the left. And let's see what we get. We get X at the top. What does it look like on the left now?
Z.
Z here, right? On the left, we have a Z. And on the left of that, we're going to have...
Looking at this picture.
Right. On the left of that, we're going to have a Y.
Shai?
Yeah.
Sorry to interrupt, but back over to case 3. Is that... I'm looking at the right, and is that left colored right? Or should Y be black?
No, I think Y should be red.
Does that, but going down from Z, you have
You have the
two
same
different
number
lines.
as you had before.
You have the same number as you had before. Oh, Heather's noticing that this side you have 2 and then onward, and this side you have 1 and then onward. But that's what you had before, and if it was balanced before, it stays balanced now. Right? Right?
Okay.
I see what you're thinking, but... Right.
Okay.
You assumed it was balanced before, so now it stays balanced the same way. Good question. All right, now you have to help me here because I got lost track.
Rewrite what you're doing.
zy, oh yeah, I know, but z, the a comes down here, the z gets c over here. Where's the b go? Over here on the y. And this is a u and a d and an e. And now let's color it. R, R, B, B. You don't recolor anything here. You just rotate it in place to make the next one work. Now this clearly doesn't affect any of the distances, because we haven't moved any blacks out of the way they were before. And it does maintain a red-red clash. But it puts us in a position where we can kill that red-red clash and maintain the distances at the same time. So goodbye Fluffy, hello Spiky. Good? Convincing now? All right, so the minute you get that black on top, you're done. And that's why at the end of all these rotations, if the red-red clash pops all the way to the top, we always, kind of as customary, turn the root into black. As if to say, I'm done. All right. We'll do graph algorithms starting tomorrow. Problem set 1 is due today. So if you have questions, please ask me. I'm happy to help. Problem set 2 is open for business tomorrow. And I would like to have it finished by the end of this week. So it means a bunch of work.
Is problem set 2 available now?
It's up.
So
All right.